Hi everyone, my name is Wanji Cho and I'm from the Radio Technology Lab at Seoul National University. Today I'm going to talk about distributed MIMO systems and antenna clustering. First, I think it would be a good idea to introduce distributed MIMO systems in general. I'm sure most of you are familiar with co-located MIMO systems, where multiple antennas are placed in a single base station and used for various communication techniques such as beamforming and multiple access. In distributed MIMO systems, the antennas are distributed regularly over the entire cell. The advantage of this is that the overall cell coverage becomes better as there are lesser shadowing regions and the worst case scenarios are improved. Additionally, existing techniques for co-located MIMO systems can also be directly applied to distributed MIMO systems. Next, let's talk about antenna clustering. The problem with distributed MIMO systems is that there are many antennas distributed over the entire cell. Operating all of these with synchronized signals is not an easy task. Therefore, some of the researchers have proposed using antenna clustering and using microcells to operate the system more smoothly. Instead of operating one big cell, we are dividing the cell into multiple microcells, and each of the microcells are operated independently of each other. This is the concept of antenna clustering, where one antenna cluster is its own independent microcell. Although our research is still in its early stages, the problems we are trying to tackle in distributed MIMO systems are as follows. Since distributed MIMO systems distributes antennas over the entire cell, sending non-synchronized signals can cause intersymbol interference. We're trying to analyze the effects of this by using delay profile analysis using ray tracing simulations. Also, to use distributed MIMO systems efficiently, timing advance for distributed antennas, as well as antenna clustering to prevent ISI is also considered in our research. The first part of my research is the delay profile analysis for downlink outdoor scenarios, where we considered various distributed antennas placements and their delay profiles. In 5GNR, there are many flexible numerologies that can be deployed, meaning that according to the numerology, there are various symbol and CP durations. In the graph shown on the left, you can see that for each of the numerologies, the subcarrier spacing is different, meaning that they each have their own symbol duration, and accordingly, they all have different CP durations. The CP duration in meters shown on the bottom of the left graph shows the distance traveled by the electromagnetic wave in the CP duration time, which means that if any of the excess delay is to exceed the CP duration in meters, it can cause intersymbol interference. Thus, the subcarrier spacing affects the allowed maximum delay for each of the distributed antennas. To conduct the delay profile analysis, we considered downlink outdoor scenarios in urban environments. The map data used was that of Seoul Gwanakgu, and we considered mainly two deployment scenarios, the urban micro scenario and the urban macro scenario. The urban micro, which is abbreviated as UMI, has an intersite distance of 200 meters, and we considered 160 user antennas. For urban macro scenarios, the intersite distance is 500 meters, and we considered 1,120 users. All of the users and the transmitting antennas were distributed according to the uniform random distribution. By obtaining all of the excess delay profiles of all of the users, we were able to obtain that the absolute excess delay PDF followed the gamma distribution, with the specific parameters of the gamma distribution being different for the deployment scenarios. We only considered paths within 30 decibels of the maximum path power, and as you can see in the figure on the left, as the numerology increases, the CP length decreases, meaning that the allowed absolute access delay is decreased as the numerology increases. By taking a look at the CDF of the absolute access delay, we were able to obtain the probability of the access delay exceeding the length of the CP. For urban micro scenarios, there was 0% chance that the access delay would exceed the CP for all numerologies. However, for urban macro scenarios, for numerology 2, there was a 27% chance that the access delay would exceed the length of the CP. And if the access delay exceeds the length of the CP, it is possible for intersymbol interference to occur. If the same data is transmitted from each antenna, and the access delay can exceed the CP length, which can cause intersymbol interference, this can have a negative effect on the communication link. To analyze the impact of the access delay, link level simulations were conducted. Since we have seen in the previous experiment that the delay distribution follows the gamma distribution, we used the gamma distribution to create artificial delays for this experiment. We also considered two bandwidths, 20 MHz and 40 MHz, and the channel was assumed to be Rayleigh fading channels. We also considered three modulation schemes, 16 QAM, 64 QAM, and 256 QAM. Both of the urban micro and urban macro scenarios were considered. By conducting the link level simulation, we were able to obtain the BER to SNR graph for each of the scenarios shown in the previous slide. For urban micro situations, the access delay doesn't exceed the CP and no performance loss is observed. For urban macro scenarios and for numerology 2, there was a 27% chance that the access delay exceeded the CP and intersymbol interference occurred. The BER loss is dependent on the QAM order used in this experiment, as higher modulation order resulted in higher performance loss, as it can be seen from the top side right figure. As for the bandwidth didn't have any effect on the observable performance loss. To combat the previous result of performance loss due to intersymbol interference, we considered antenna clustering based on distance. As the absolute access delay is more likely to get longer as the cell size increases, we thought it would be logical to divide the cell into multiple antenna clusters with smaller cell sizes. Our goal was to prevent any of the access delay exceeding the CP. However, there are more metrics to consider other than distance for antenna clustering, such as the average throughput of the overall system, as well as the signal to leakage ratio, which is the power ratio between the in-cluster transmission and the out-of-cluster transmission, as the out-of-cluster transmission is considered as interference for all of the nearby clusters. We can state this problem as an optimization problem, where we are trying to maximize the data rate in each of the clusters without having any of the clusters exceed the CP length for its access delay. We are also trying to meet a certain data rate threshold for each of the clusters, meaning that we are assuring the users are met with a certain quality of communication. As this is still an ongoing research, this is the main focus of our future works. For antenna clustering, we are trying to use more various metrics such as the pairwise antenna SLR and the overall data throughput to see which of the clustering methods work the best. For the ray tracing, we are trying to use more diverse urban environments for delay profile analysis, where the environments have various building heights and building density. There's also the additional problem of synchronization, as each of the antennas using local oscillators requires synchronization before they can be optimally deployed. This concludes my presentation, and I thank you all for your attention.